Elena and I are talking about the law of equilibrium. Elena, just imagine this simple, hypothetical chemical reaction denoted by this equation. We can define for that reaction a mathematical expression, as it's written up here, the concentration of C to the power 2 divided by the concentration of A to the power 2 and the concentration of B to the power 1. And we give that mathematical expression a symbol Q. At equilibrium, the numerical value of Q, we give a symbol K. So we can write here that this expression numerically is equal to a number, for which we use a symbol K, and we call that number the equilibrium constant at any defined temperature. So how do you interpret that statement, this law of equilibrium?
Well, if we have a reaction mixture at equilibrium, then the numerical value of that expression remains constant, and it doesn't change as time passes.
Why doesn't it change as time passes?
Well, that's obvious. As long as C and A and B are all constant, then the value doesn't change either.
Okay, and it's one of the characteristics of a system at equilibrium that the concentrations of these species don't change. Good. But hang on. If the concentrations of those things don't change, isn't it true that any mathematical expression involving these concentrations would be constant over time if it's at equilibrium? So, for example, what about the numerical value of that mathematical expression?
Well, if B and C are constant, then that expression is constant as well.
Absolutely. And this one, for example.
Again, it's obvious. As A and C are constant, that expression remains constant.
Beautiful. And just one more. That one.
Well, it's obvious now that any expression containing any of A, B, or C remains constant, even if it remains all of them. So it will always remain constant with time.
Aha.
So what is so special about this one then?
That's the question. What is there special about this mathematical function as distinct from any other? Exactly. And to make that point, we need to go from, we've been thinking about a reaction mixture, we need to go to thinking about visualizing not just one reaction mixture, but more than one. Perhaps 3, perhaps 153, whatever. I'll just use 3 for example, and I'll label them 1, 2, 3. Now, in that, if the reaction is at equilibrium in all of those, and they're at the same temperature, then this is constant over time, this is constant over time, this is constant over time, this is constant over time. But the value, the numerical value of this mathematical expression is the same there, there, and there. Whereas the mathematical expressions, any other mathematical expression is not the same there, there, and there.
Aha, I think I understand.
Well, let me just try to clarify with some simple numbers, which I've already put up on the board. I'm representing here 3 reaction mixtures, which have got different concentrations of A, B, and C, but they're all at equilibrium. In reaction mixture 1, the value of Q is 100 squared divided by, on the bottom line, 10 squared times 1. That comes to 100. In reaction mixture 2, 6 squared divided by 1 squared times 0.36. That comes to 100. And in reaction vessel 3, check it for yourself, 20 squared divided by 0.2 squared times 100 is 100. So the magical, marvellous thing about this particular mathematical expression is that it's the same there, there, and there. And this particular value is the thing that at that temperature we call the equilibrium constant. What about, let's take, for example, we could take any mathematical function other than this one. We'll use this one, it's simple. We'll do this checking. I've got some numbers here. The value of that mathematical expression in reaction mixture 1 is 0.10. Sorry, 0.010. In reaction vessel 2, it's 0.060. And in reaction mixture 3, it's 5.0. So even though this value doesn't change, this value doesn't change, and this value doesn't change, in that mixture, it's not the same value in each mixture. And that's the key element about this remarkable function Q.
Aha, so I get it now that the law of equilibrium is much more profound than I thought.
This is an extremely profound meaning of the law of equilibrium. Yeah. Thanks. Nice talking with you.
Well, thank you.